Let's start with Dr. Carrie Brown. She specialized in decarbonization and resiliency for the lens of policy research, program design and evaluation, codes and standards, and other technical consulting. Her expertise is in the field of building science, mechanical engineering, simulation and optimization methods, and data analysis. She is active in ASHRAE and the International Building Performance Simulation Association, where her roles include ASHRAE Society Director at Large, ASHRAE Center of Excellence for Building Decarb, and immediate past president of the IBSA in a USA branch. So let's all welcome Dr. Carrie Brown to the stage. Yes, so also at the end of each presentation, there'll be QR codes that will come onto the screen. Please initiate them and fill out the form so we can get some valuable feedback. And for the PDHs.
Great, thanks Scott for the introduction. So on the screen, we have the learning objectives for the PDH credits. We'll be going through the questions later today. I want to start with an acknowledgement that a lot of the talk today is based on a study that we did that was funded by NYSERDA. The study was called Assessment of FTMI Data Files. This was done between my company, Resource Refocus, and University of Buffalo, managed by Amanda Stevens. And if you're interested in learning more about it, the technical report is on NYSERDA's website, and we also published a conference paper. So the overall scope of the study, NYSERDA wanted to understand what type of weather data are they using across their, all of their programs. And they wanted to understand, should they be considering switching to different formats? And if they want to, what are the implications? What does that look like? So, oops. Is that still okay? Don't know how to get that to stop. Well, you should be seeing a graph that shows a spiral of temperature, and it's not playing right now, but the way that it works is there is something called the NASA temperature spiral, and it starts at 1880 and then goes all the way through and shows you how the temperature is changing over time each year since the pre-industrial times. And what we saw is that for the first time last year, we crossed the 1.5 threshold for a single year. And in this case, we're not talking about long-term 1.5 change we're trying to avoid for the IPCC, but it is a concerning thing. So today is actually my birthday, and if you're wondering why I'm here on my birthday talking to you about weather data, for one, I personally think it's a riveting topic, but I also think it's something really important that we as the industry should be thinking carefully about. The climate crisis is not some future thing. We're in it now. We're already seeing increase in intensity, duration, and frequency of severe events, and these are posing major risks to both the occupants and the buildings that they're in. So my question is, should we still be using historical data to design the buildings of the future? Quick level setting, just so I give the right amount of detail. How many folks in the room use building performance simulation in their day-to-day work? Okay, and are we familiar with TMY weather files? Some. Are we familiar with psychometric charts? Okay, great. So for those of you who aren't familiar with TMY weather files, this is what basically every building performance simulation program uses. It's a comma-separated file. It's a very standard format. It has things like dry bulb, humidity, things like that. The most common typical meteorological year, TMY file, the thing to know is that it is a composite of multiple years. And so they'll look at, often it's a 30-year time period, but it could be as short as 7. And there's an algorithm that looks and picks like, what is a typical January? What is a typical February? And of that 30 years, it kind of Frankensteins these into a single year. Some of the weather files that are in use right now, so TMY3 historically has been the most common. This is using data from 1991 to 2005. More recently, we've released TMYX files, and so this is using data from 2001 and forward. It's also using satellite data for solar, which is a major improvement from before because it used to be modeled data. We also have actual meteorological year, or AMY, and so this is a single historical year. This is often used for M&V analysis. We have extreme meteorological year, XMY. This is very similar to TMY, except the algorithm selects for an extreme condition, either hot or cold, rather than a typical condition. And then the emerging work is for future TMY data. So this is an attempt to predict or give a representation of what the future might look like. Availability, TMY3 is readily accessible, has been for years. TMYX, Climate.1 building is a great resource that has weather data from around the world. In New York in particular, Resilient Buildings is a good resource. It has some of all of these types of weather files for if you're looking for, New York specific analyses. And then for FTMY, this is a very active field of research. Some countries have released them. And when I finished my work on the NYSERDA project a few years ago, one of our findings was that we really need better data. But even in the past few years since we finished that, a huge amount of future weather files have become available in the industry. So not all future weather files are created equal. There's sort of four main groups of the ways that these can be developed. And I'm going to walk through them in increasing complexity so you can kind of understand the range of things that are available. So the first one is an analog scenario. This is where you find an existing location, and then you give a representative existing location that will align with what the projected future is. So in this case, you can say, okay, in the future, New York's going to feel like Arkansas. And this is a really powerful technique because people can picture that. They can understand that, New York is really different from that they can grasp that. So it's a great way to communicate. But for the, purposes of building simulation, building analyses, it's just not accurate enough. There's lots of things wrong with it, not the least of which is that the sun is in the wrong place. So yeah, the next one up is morphing. This is something that's been around for at least 20 years. If you have seen sort of future tools over the past couple of decades, it's probably morphing. And this is the case where you just stretch or shift existing data. This is a really simple method. It doesn't take a lot of data. You can apply it to any existing weather file, but there have been recent concerns on the accuracy of this. So the crux of the concern is that you're applying linear transformations to a very nonlinear coupled system, and that you're going to end up with a situation that's not psychometrically accurate. Said in a different way, you get weird combinations of temperature and humidity, which can really affect your building design. Also, if you're just doing these simple stretching and shifting, you're not going to see those changes in intensity, duration, and frequency that I talked about earlier. The next step in complexity is statistical or stochastic methods. So this is kind of like morphing, except there's much more complicated adjustments. And so you take historical data, but you generate synthetic weather. You can get the more extreme conditions than what you've seen in the past. And it produces a wider range of projected future scenarios. It is still relying on historical data, though. And a quick illustration of how morphing and statistical methods might look different. So in the upper left-hand side, that's your TMY3. That's the typical baseline older weather data. The next three across are examples of statistic examples. So these are box and whisker plots. The sort of inner quartile is the box, and then the outer quartiles are the whiskers. And then the next three are three examples of morphing. And what you'll see is for the TMY data set and the morphing, if you look at March, you've got that warm spell that appears exactly in the same place in all of those files. So you just took the file and shifted it. Where in the statistical ones, you do get some of these extreme examples, but it's not in the same place. And then finally, the last is dynamic downscaling. This is the most complex of the proposed methodologies. This is a physics-based method, and it is using global climate models or global circulation models. This is not bound by historical data. The data remains physically consistent, so it is psychometrically accurate. The problem is it creates huge data sets, very powerful computation required. We're talking weeks on a supercomputer still, so it's just not something you can do from your laptop. There is sort of a nod to the future talks. There is some work looking into using AI to do a better job at creating these weather files. And they are having good results with the near-term data. So, the 7 to 10-day forecasts are working quite well. They can use low-resolution data, and the computational needs are actually less than what today's weather forecasts need. But the climate modeling for the longer term is still very early stage. This is a much more complex problem. And, one of the main challenges is that the inputs are changing all the time, both the temperature and the carbon. So as I said, when we finished a few years ago, we were really lacking in available future weather, especially in the US. But right as we were finishing, the National Lab started a big project trying to get us better data. So there's a 3-part project that says till 2023, but it's actually still going on. Argonne is doing that heavy computational downscaling, and they're creating single future weather files. Oak Ridge is working with them and taking that data to make future TMY weather files. So looking at, for a collection of future years, what's a typical year? And then Sandia is looking at making extreme future weather files. So trying to project that extreme cold or hot. And one interesting thing about the ORNL, and this is the data that I'm using later in the talk, in addition to doing the TMY algorithm across multiple years, they've also created versions that do it across multiple climate models. So, if you're looking at 6 of the main climate models and you're not sure which one is the right one for your analysis, they give a version that sort of puts them all into one so that you can look at a range of possibilities. This is a little bit of an aside, but I think it's also important when you're thinking about weather files. One of my other hats at ASHRAE is that I chair TC 4.2, which is the Climatic Information Technical Committee. And this is the one that oversees the standards that sets the ASHRAE climate zones. For those of you who aren't familiar, the ASHRAE climate zones, they have a number 0 through 9, which represents temperature from cold to hot, and then a letter ABC, which is the moisture component. We're about to release a major update to the assignments, and this is a chart of all the counties in the US that will get a new assignment in this release. I do want to emphasize that some of these changes are because the climate is changing. Some of it is because we're actually changing the way that we're doing the data. It used to be that there was some expert opinion in assignments for things like the moisture zone, but now it's completely data-driven. And here's the same information, but split so that you can see on the left-hand side, that's where counties are changing because the temperature is shifting. And on the right-hand side, you can see that's where they're changing because of the moisture conditions. And the way that the map works is basically the whole right half of the country is called moist. The left side of the country is called marine. And then historically, the middle of the country was dry. When you look at the recent data, that whole middle of the country, there's large parts of it that are now being assigned to the more humid climate zones. So for the NYSERDA study, we did an extensive lit review, a lot of interviews with folks at NYSERDA to understand what types of analyses were using weather files. And then one of the things they were interested in doing was looking at, okay, well, if we look at all the available weather files right now, what would it look like for a simple modeling case? And so we picked an envelope-dominated building, specifically an all-electric single-family home built to 2020 residential code. And the idea is we wanted to pick, what does a typical new residential building look like in New York under these different conditions? Here are the results of the analysis. So these are stacked bar charts. At the top is heating and cooling in red and blue. And going across the results, the left-hand side is the TMI3, so that's our baseline file. This is the one that has historically been used in codes and standards and programs. The next bunch across are the TMIX, so these are the more recent data. And then you have the extreme cold and extreme hot years, and then two sets of future weather file examples. The first one is a stochastic example, and then the next three are a morphed example. And this is an example in Buffalo, but we ran the analysis in both Buffalo and New York. And across the board, what we're seeing is that as you move forward in time or into the more extreme climate projections, we're seeing an overall increase in energy use intensity. And this is happening with a decrease in heating at the same time as an increase in cooling. But that decrease in heating is outweighing the increase in cooling. So you're seeing lower energy use over time. Here's the same information, but looking at peak demand instead of overall energy use intensity. And a reminder, this is a heat pump example, so we're seeing a winter peak. But the differences are quite substantial, which could have implications when you're sizing systems. In this case, in almost all cases, we saw peaks in the morning, except for one of the white box examples. And this is just a result of that stochastic nature of the files, that in that particular file, you had a real cold snap at a different point in the day. But again, same as the energy use intensity in general, as you're moving forward in time or more extreme scenarios, you're seeing a significant decrease in the winter peak demand. Here's the same information, but in emissions. And so in this case, the Energy Plus file is the darkest one, and then the dotted line on the top, this is the extreme cold file. And so what we're seeing is that across the board, the future weather files and the warmer weather files have noticeably lower emissions in the winter months. And then over the summer months, they're pretty similar. Here's the same information, but just say cumulative over the year. And so that you can see from, January until the end of December, for those cold examples, you end up in a quite different spot. And so, there's not necessarily a right or a wrong, but it is important to see that people using weather files that are available today can get to a very different place in their analysis depending on which one they choose. So for this limited analysis, this was a single example of a residential building in New York. We saw decreased heating, increased cooling, and it was more pronounced in Buffalo than New York City. This is an all-electric example, and so we saw a winter peak and a general shift from heating into cooling. If we looked at a mixed fuel example, when the peak demand might be driven by air conditioning, in that case, we would probably see an increase in peak demand over time, assuming that the peak is still happening in the summer, which in New York, it might not be. So the next thing we wanted to understand was, okay, we have a sense of what it looks like from an energy perspective, emissions perspective, peak demand, but what does this mean for the available passive strategies for a building like this? And so the next part of the analysis is we looked at a psychometric chart analysis and looked at two different sets of passive strategies. The first was just simple adaptive comfort, that you're changing what you're wearing in the building to see how comfortable you are. And then the other was looking at the available passive strategies for the building design. Can you use evaporative cooling? Can you use thermal mass and night ventilation? Things like that. So here's an example in New York. The left-hand side is 2000 to 2019, and then the right-hand side is a projection for 2040 to 2059. And this is using those ORNL examples. In the study, we did this for all of the weather files, but I'm not going to walk through them today. For those of you who aren't familiar with psychometric charts, I could talk to you all day long about how cool they are. But I think the important thing to know is that across the bottom, you're increasing in temperature, and across the right-hand side, you're increasing in humidity. So the bottom left is cold and dry, and the top right is hot and humid. And in this case, we're seeing a notable shift from the cold and dry up into the hot and humid. Here's the same example for Buffalo. similar to New York City, we're seeing that general shift. And then I recently gave a talk in Oregon, so I included this example just so you know it's not just New York. This is also happening in milder climate zones. And in Oregon, what you're seeing is you're not quite getting up into those hot and humid numbers, but you are significantly shifting into hotter territory. And so, and I guess I should say, for all of these, the little shapes are where the passive strategies are available. And so what we did is we tallied all of the hours in the year for each of the weather files in which these passive strategies were available. And so the, you can look, you have the comfort one. So are you wearing a tank top? Or are you wearing a sweater? And then all of the others that are more building design oriented. And what we're seeing is that sort of until you get way out into the future, interestingly, the total number of available passive strategy hours is increasing over time or with increasing climate conditions. And in general, like with the UI example, we're seeing a decrease in the available heating strategies and an increase in the available cooling strategies. This is the same information, but showing the difference from baseline. And so on the bottom side, you can see all of the ones that are decreasing are heating strategies. And one of the ones that is most noticeable is that the passive solar heat gain is becoming, very, very little available hours for that strategy. And so in this case, I'm not worried if in the future people are going to wear more tank tops than sweaters, but I am worried if you design your foundation and your envelope that's optimized for passive solar heat gain, and you find out that a few decades in the future, your building should not have been optimized for that. This is the same example in Buffalo. So we see a similar trend, increasing passive strategies over time. Same thing here, increase in the cooling strategies, decrease in the heating strategies. And again, you're seeing, a noticeable change in that passive solar heat gain as well as the evaporative cooling. And then here's the same example for Lane County, Oregon. And in this case, they had an even more noticeable difference in the passive solar heat gain. With today's climate or using recent weather file, it would have made sense to really optimize for that passive solar heat gain. Several decades in the future, it probably won't. So in general, what we were seeing was that the later or warmer files generally result in a higher number of passive strategies, and there's a shift from heating to cooling strategies. To complicate things further, when you compare the different future weather files, the specific distribution of the available strategies is different depending on which one you pick. And I don't know which one is right, but I am worried that we're using data and we don't know which one is the right one. So overall lessons learned, in doing our lit review and in talking to lots of experts and folks at NYSERDA, one of the most common challenges that folks noted is that this is a major collective active action problem. I think people generally agree that we should not be using data that, dates back 30 years. But if we want to switch, there's lots of stakeholders involved. For NYSERDA in particular, if you change what is being analyzed for the codes and standards program, hopefully you would also then be changing that for the programs that are reliant on those codes and standards in the future. But those are heavily reliant on third-party programs. So if they wanted to do that, they would need to be, coordinating with ICC, Energy Star, Passive House, things like that. And I don't think any one of these entities may disagree, but getting them all to jump at the same time is difficult. One of the other things is that it became very clear just in the last few years that the available data has outpaced the guidance. There's lots of weather files out there, they will run, and so I think people will use them. And whether they're using the right ones for the right application is a real concern. And these standardized protocols, we need guidance on both how to create the weather files and how to use them. I would like for folks to understand the difference between a morph data set and a downscale data set, but when you're just looking at the file, you can't tell the difference. ASHRAE is providing some guidance on this point, but it is limited. So we're releasing a major update to the Fundamentals Handbook. Chapters 14 and chapters 36 have some information on this. Standard 209, Building Performance Simulation Process, did include an informative appendix on future climate analysis, but it's more high level. It's not getting into the nitty gritty of like, what do you do today for your analysis? And then TC 4.2, which is the one that I work on, we are in the process of proposing a guideline development for integration of future weather data and calculations for the built environment. I think across the board, we saw, even in this room, we don't agree on what the right answer is. So let's put our heads together and actually write this out for the industry. What types of analyses are affected? And we were looking at this in the lens of NYSERDA, but I think this is sort of true across the industry. So one of the big things is this sort of interplay between fuel switching and peak loads and resource planning. As we saw from the limited analysis, there's the potential for a significant shift in HVAC loads at the building level, but in opposite directions seasonally. And with electrification, we're likely to see an increase in both the winter and the summer loads where people are using electric for heating for the first time. And then many folks in places like New York are introducing air conditioning for the first time. For codes and standards, most places in the country rely on TMY3 data for codes and standards. California is one exception. They use TMY-X data for their recent, and in the next version, they're likely to use future weather files. But most codes and standards are using the data that's looking several decades in the past. And when you're doing that, codes and standards are optimizing for energy, but also looking at emissions. And if you're trying to calculate the lifetime operational emissions, it's really difficult today because you've got a warming climate, you're shifting from gas to electric, and the electric grid is changing all at the same time. So this is sort of one of my personal, passions, but looking at adaptation and resiliency analysis. So with warming trends, we're high level expecting to see strongly cooling dominated energy use. If you're in a climate that's highly cooling dominated, you think energy is going to go up because air conditioning loads are going up. If you're strongly heating dominated, likely your total energy use is going to go down. The hours of passive strategies may increase over time, but the available strategies are also shifting at the same time. And so, my main concern is that if we're looking backwards to design resilient buildings of the future, even with the best of intentions, we may select maladaptive solutions. And, I'm not talking about people being uncomfortable. I'm talking about fatalities. Extreme heat events kill more people every year than any other natural disaster. And heat stress deaths are seen disproportionately in BIPOC communities and frontline communities. So these are the, communities that are in most need of help, and they're going to be the most affected in the future. So our designers need guidance now for decisions that are going to support future-ready design. We want resilient design that's going to be, supporting passive survivability so people can safely stay in their homes or other buildings during an extreme event. And we want it to be able to withstand both the sustained stresses, so general increases in temperature over time, as well as the shocks, those extreme events that we're seeing more and more frequently. And when you're making these decisions, I think it's really important that you consider the expected useful life of the component parts of the building. So the weather file that you're using for your HVAC system that lasts 15, 20 years is probably different than the weather file that you're thinking about for your foundation and your envelope design, which is going to last many decades into the future. And so think about how long that component is lasting and then pick something that has an appropriate level of risk. So in conclusion, as climate change risks grow through the century, design decisions and adaptation retrofits and new construction should use the weather files that are based on the appropriate climate projections and hazards that align with the systems you're considering. We definitely need industry guidance on protocols, but implementing these protocols will require extensive collaboration touching a wide range of stakeholders. And so that's what I have, and I'm going to hand it off to Brian, who's going to talk you through things more from a commercial example. Thank you.
Thank you, Carrie.